Everyone, this is Yash, and today we'll be looking at the daily question of 25th June, that is kth smallest product of two sorted arrays. Given two sorted zero indexed array nums1 and nums2 as well as an integer k, return the kth smallest possible product of nums1 into nums2j, where 0 is less than equal to I and I is less than nums1 dot length, and 0 is less than equal to j, and j is less than nums2 dot length. So what the question asks us is, let's just use the first case to describe it. We have two lists, num1 and nums2. So the possible products are 2 into 3 6, then 2 into 4 8, then 5 into 3 15, and 5 into 4, that is 20. So the question asked for kth smallest product, that is, for this case, second smallest product. So the second smallest product will be not 6, 8. So we return 8. That's the basic approach. So what we are going to do here is, because the test cases are really large, we can't go for an m into n approach and then calculate all the values first and then just iterate it later, because this will be a 10 to the power 8, I guess. Yeah, 10 to the power 8 operation that will take way longer. So instead, we will use a better approach, that is binary search. First, long left. Our value of left will be minus of power 1, 10 to the power 10, and our right will be power of 10 comma 10. Why so? Because we have the values 10 to the power 5 and minus of 10 to the power 5 as a cap. So the maximum value that we can get is 10 to the power 5 into 10 to the power 5, that is 10 to the power 10, or the counterpart for the negative, or we can get the minimum value as minus of 10 to the power 5 and 10 to the power 5. So simply just take two values left and right, and the algorithm for binary search, that is by left is not equal to right, what we are going to do is long middle. Why we are using long? Because the values are 10 to the power 10, way above the limit of our normal integer. Long middle equals to left plus right minus left by 2. Here we get the middle value, and we are going to pass it in a helper function. Let's give the helper function a name, that is less or equal values. Okay, we are going to calculate the values that are less than and equal to our value, and we are going to pass our middle, our nums1 and nums2 here. And based on that approach, what we are going to do is we are going to calculate the values that are equal to the middle value that we calculated, or less than the values. So less or equal values. And if the values that we get, the answer that we get is low, that means we need to push the boundary of our left. So we will set it as middle plus 1. Else simply right equals to middle, because why we are not doing this right equals to middle minus 1, because right could possibly be sitting on the answer itself. So we want it to reach left, because left won't increment if it's on the answer, but right will. Then return right. So this is the basic binary search approach that we are going to use based upon the value that we have on the index. So that like we are assuming that the value that we calculated is the answer and iterating around it to find the value. Okay, and here we are going to put task A. Okay, so this is done. Now let's calculate the another part, that is our function, that will be long less equal values. And here we are passing our long middle and vector int nums1 and nums2. Okay, these three values we are catching here. Done. Now what we are going to do is let's initialize a few variables, that is our counter. Here we are going to store the values that are less than or equal to, and a size for nums2. I just initialize a size variable because I think it's better for the compiler to directly access the memory rather than doing the arithmetic operation. Now for auto itr in nums1. Okay, so let's check if the value of itr is 0, because we can only have three cases: either it's 0, or it's less than 0, or greater than 0. So if the value is 0, then the possible outcomes that we will get is count plus equals to size. Now when are we going to use this operation of count plus equals to size is if and only if, just a second, we have to use it here. Uh, so we will use this operation if the target value that we have, like the target provided, is either equal to 0 or greater than 0. Only then it will be inclusive. Let me just explain. We have -1, -2, comma -3, and 0, 1, 2, 3, and 4. So the values that will be included will be, let's just say our past value is 0, itr is equals to 0 at the moment, and our target is let's say 3. Okay, so the values that are going to satisfy this condition are going to be, that is itr equals to 0, then we are only going to add the size if the target is positive. Okay, target equals to 3. So let's write the condition: if our target is greater than equal to 0, then we are going to add the size, because multiplying all the values here we have, like this -1 and -2 and -3, all these value when multiplied by 0 will result into a 0. So the index that we will get is like this: 0 and 0, all zeros. So there is no point just iterating through all the values and finding a middle. We will directly assume that if the itr is 0 and the value provided is positive, or it is, let's just say the target is 0, then all the values are going to be either equal, or no, there is no other case. If the target is 0, then all the values are going to be equal, because anything multiplied by 0 results into a 0. But if the target is positive, then we are including the values that are less than our target. So multiplying all of these by 0 will still result in a value that is less than the target. That's what approach we are using here. If the value is 0, then target should be greater than or equal to 0 to add. Now let's initialize our second binary search, that is left equals to 0 and right equals to size. Okay, what we did here is we used another approach for the nums2. Why? Because we have to tackle the conditions in which -2 into -3 will result in 6, and -1 into -1 will result in 1. So as you can see, the values of negative when multiplied together result into a positive. So we have to deal with those values. How we are going to deal with it? We will use a while loop. Simple approach: while left less than right. Now we have two cases here. Okay, first let me calculate the middle. By 2. Okay, so why did I use middle equals to left plus right by 2 here, but this left plus right minus left by 2 here? Because the value can exceed the long limit here, but it won't happen here because the test case provided is in the range. Okay, so in middle equals to left plus right by 2, we get the middle value, and we are going to calculate our product. Let's name it as prod equals to long itr multiplied by nums to middle. Okay, now we have the multiplication of the index that we are using at the nums1 and the current index of nums2. Like we will iterate through middle values in nums2. Long product equals to, okay. Now if we only have a few cases here, if our product is greater than target, right? If our product is greater than target, or else it's not, it's equal, or I don't know, less than. So what we are going to do, if our iterator value is greater than 0, that means if the value that we passed is greater than 0, that means we need to move our right. Why? Because if the product is greater and the value is positive, that means we need to move the pointer from the right side to the left side because we need to decrease the values. But on the other hand, if we are facing negative values in our case, then we need to move our left to forward, because again, a larger negative value multiplied by another large negative value will result in a positive value. So we have to tackle that situation here. Now another loop, another case, if ITR is greater than 0 here, or it's not. So what we are going to do, again, just use this as a base approach. Let's just remove this from here. Okay, let's say it's not here. If the value is greater than target, what we do, we move our right equals to middle, right, and else we move our left equals to middle plus 1. It's a modified binary search. We are not dealing with equal conditions, but it's only working for positive values. Why? Because, well, it doesn't check whether the value that we use as ITR or nums to middle is negative, because two, as I said earlier, two large negative result into a positive. So what we do here, just simply make it a condition that if our ITR is greater than 0, then we have to deal with this. ITR greater than 0. If it's not, then the other cases will run. That is, this part will be run here, and this part will be run here. You see, the negative updations will be done in opposite manner to the positive updations. That's what I am trying to do in the same loop. If the values are positive, it will run this part. If it's not, then it will run this part. You can do this part in another else condition using another if else block. Let's try to run. Oh, wait. Not done yet. My bad. Okay, so while loop is over, now simply add the values. What will the value added be? Count plus equals to. We are here going to check whether the value of ITR is greater than 0. Why? Because if it is greater than 0, that means we are including the lower bound range of the index that we targeted. So simply adding left. If it's not greater than 0, then it's going to be nums size minus left. Okay, I will show the dry run after this because I know it's a difficult part. Target. Oh, wait. This shouldn't be middle because we are using another middle here. What's the error? Okay. Right back to long middle. Long typecast should be here. Greater than ITR should be greater than 0. Right equals to middle, left equals to middle plus 1. Else ITR greater than 0, left equals to middle plus 1. And right equals to middle, count plus equals to ITR greater than 0. Okay, not this. Okay, I found it. What we did is we updated count every time the while loop was going, but it only has to be updated once the while loop ends. Like we calculate the value of the left where it should be, and then it updates. Yeah, let's use a edge case that could just solve this. 2, 3, 4, 5, comma 1, 3, 4, 5. Yeah, add it here. Okay, I think it should work on majority cases now. Yeah, let's try to dry run this. We will use this test case that is -2, comma -1, comma 0, comma 1, comma 2, and -3, comma -1, comma 2, comma 4, comma 5. Okay, so what we did here, first the main code, that is this part. Let's set few values here. Main left equals to 1, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then right equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, left and right are written here. And what we did here is calculate the middle. Left should be negative. For the first part, middle is going to be 0. So what we did, we passed middle, and all the values that are less than or equal to 0 should pop up here. Okay, so we come here, we iterate through the first index, that is -2, select it, and from this part we check it's equal to 0. No, but it is negative. So while we are going through the loop, we simply check if the product, what will the product be. -2 into 2, for this case the middle value will be 2 for the current scenario. That is going to be -4. Now -4 is less than our value. Yeah, so this part will run. Right equals to middle, right will come here, and our next middle is going to be -1. Now -2 into -1, it's going to be 2. 2 is less than middle. No, it's greater than middle. So we again update it. Since the value is greater and it is negative, we are going to move our value is greater and it's negative. We are going to move our middle left equals to middle plus 1. So it will come here. So we have two indexes that will work for the test case. That is, we are going to add them. So the value is added in the count. Now we move on to this and repeat the same procedure for each and every value of this array, and calculate all the values that are less than and equal to in this array, but using binary search. How? Calculate the middle, find the middle, calculate the product, check if the value is greater than or less than, and use the conditions. I can't demonstrate it very well, I don't have the equipment to write it, but that's it for today, guys. Thank you, and do check out the link in the solution, link of the solution in the description.